Hi, welcome to another lecture on Power MOSFET switching characteristics. Okay, lately I've been working on high-speed switching applications, so I have learned quite a bit. One of the things that I want to relay or make you aware, especially if you're beginners, or in other words, straight out of college and are only familiar with MOSFETs characteristics. If you do power MOSFETs, they act different, or there's slightly difference. So I want to point out the differences, which will make your life a little bit easier, and that's what this video is for. Okay, so basically I'm gonna show the difference between when you're simulating and working with power MOSFETs and CMOS. Okay. Besides Z-speed, high voltage, the switching characteristics are a little bit different, and you calculate them a little bit different. Okay. So what I'm going to do is I'm going to use the example that I use in my video, which is how to model a MOSFET, basically a MOSFET. There's a video on my channel, you can look that up. And on that one, I modeled the IRF 624 using the data sheet. Okay, so go ahead and watch that first before you watch this, or if you think that you have the background, go ahead and continue watching this video. But anyway, on that video I show how you can use the curve plots, and by using two equations you can calculate the threshold voltage and your KP. So these are the two that you need for your DC operation. Okay, and then there's three parameters that are in the data sheet, which are CISS, COUTSS, and CRSS. And with those, we calculate CGD, the capacitance from gate to drain, which is often called as the Miller cap. And also CGS, which is the capacitance from gain to source. Okay, so let's go ahead and show you this quick how to test for the switching circuit, how to test the switching characteristics. Okay, and for that we use the data sheet. Okay, there's this test circuit, and let me see if I have the data sheet here. I do not. Okay, let's see if we can find it. IRF 624, and I believe I used the Vishay data sheet. Okay, and I want to point out, this is where I got the input capacitance, output capacitance, and the reverse. These are the three parameters, and then I calculated what the appropriate capacitance is. Okay, so here we go to where it says fault type. Okay, this is TF, and it shows these parameters: VDD 125, ID 4.4 amps, RG, which is the gate resistor, RD is the drain resistor, and then it says figure 10B. So we'll go to figure 10B. Okay, so this is the switch in, but this is the circuit that they use. Okay, So if we look at that, then we'll see that this is the circuit that they're using. Basically 125 is the voltage, 28, 18, so forth. Okay. Now, if you notice, the data sheet said that the current is 4.4. And the reason it's 4.4 is because you have 125, and assuming that this goes to 0, then it's basically 125 divided by the drain resistor. You're going to have a current of approximately 4.4 amps going through that. Okay. So now before I do that, let me show you first the difference, or how a CMOS transistor would look like, or at least the switching characteristic. And in this case, it's very easy. Instead of it being setting the voltage here at 125, which the test circuit suggests, what we're going to do is we're going to set the same voltage that I'm using here. Basically, VN, I'm using a input voltage of 10 volts, okay, and a CMOS would also use a drain voltage of typically 10 volts, okay. So we're going to plot this. So we set this to 10, and this is switching from 0 to 10. So this is the characteristic that you would see in a CMOS diode, CMOS MOSFET, okay. So this is your gate. Gate starts at 0 and then goes up to 10. Now mind you, this is ramping up and should tell you that it has a very unique characteristic. Okay, it's rising exponentially, right? So this tells you that it's a RC circuit. Okay, so let's see what this the stimulus really looks like. So the stimulus is actually V3. Okay, so let me go ahead and plot or add V3. I'll add it here, and I put V3. Okay, let me move that up. That would be consistent. Okay, cut there and add it here. Okay, so that's what I wanted to show. Okay, and let me see if I can change the color. We'll say light red. Okay, so here's the input. This is basically your power supply, but then this is what you see at the gate, basically right there. So stimulus, gate, and that's what you get. And if you think about it, it's that waveform is due to this resistance and the capacitance between the gate and the source. Okay, so this is what you would normally get on a CMOS transistor. Okay, so now let's go ahead and see how a power MOSFET would look. Okay, so besides differences in the drain voltage, you can see there is a difference in the gate. Something happened to it. Okay, if you notice here, you have this little dip here. So remember, it originally went like this. Okay, let me go ahead and do another simulation just to show the difference, so you can appreciate the difference a little bit more. Okay, we'll do a parametric, and we'll say VDS. We'll do a first simulation at 10 volts, and then the second simulation at 125. Okay, so I want you to concentrate on the gate voltage, the difference. Okay, okay, see. So this would be the waveform that you would expect on a CMOS diode, or MOSFET, I'm sorry, MOSFET. But here you got this little phenomena. Okay, you got this little dip, and then this actually corresponds to right there. This should have the same waveform as that, or the same shape. Okay, but this is what I want to bring your attention to. Okay, now you notice that this dip, there's a name to that. It's called the Miller Plateau. Okay, that's the Miller Plateau. Okay, so another thing that I want you to make you aware is there's something, another thing that's very unique. Okay, and let me see if I can show that with my cursors. Okay, and it's very interesting and very useful to show this. I'm going to use a horizontal bar for this, but there's a relationship, so to speak, between the Miller Plateau and the output of your drain. Okay, do you see that? Okay, so basically right here to right there. Okay, so basically when you enter the Miller Plateau, that is when you see a transition in your drain. In other words, that's when your drain actually starts falling. And at the completion of the Miller cap, even though the voltage at the gate is rising, well, the drain has already discharged or has already moved. So basically there's no effect past this point in the drain voltage. So the majority of the change in the drain happens during the Miller cap. Okay, so that's very, very important to understand, and what is different between CMOS MOSFETs. Okay, so basically you're going to have an interval, first interval, or the start would be when VGS is 0, and then you have from 0 to the start of the Miller, that would be a second interval, and then during this time would be another interval, and then of course the last interval. Okay, so let's take a look how it looks. Okay, so basically this is what I wanted to make you aware, that by and large part that the drain changes during this time. Okay, during the Miller Plateau. Okay, and for those that drink beer, you can call it the Miller time if you wish. Okay, so in this case I want to show that there's 3 intervals. You have the first interval, that's when everything's off. You have the second interval, that's when you're charging up and you come up to the Miller voltage. Okay, and then the third, which is the Miller, and then the fourth. Okay, so basically in the first, VGS is 0, drain is 125, and your drain is 0, and your I gate is 0. Okay, so then once this turns on, in other words your source, this flicks basically is the source. Okay, and this is your gate. This one in purple is your gate. Okay, now when you enter the first, or I'm sorry, the second, your transition from 0 to 10. Okay, and during that time, okay, during the second, voltage switches to 10, and it reaches, or at final stage, at the Miller voltage, which is what this statement is. So basically it goes from 0 and it tries to go to 10, but then it stops. Basically it gets stuck or stays at the Miller voltage, V Miller, I'll call it. But again, you can make a statement. You can also make a statement that during that time, as soon as the voltage is applied, that you can quickly calculate what the gate current would be. You can assume, since you're putting 10 volts through a resistor, and basically you have the CGS 245, you can assume, and remember this is the gate, this is very simplified, you can assume that at t equals 0 that the cap is a short. Okay, and if it's a short, then you can assume this. You can say that the gate current, or the peak, I should say, is going to be 10 volts divided by 18 ohms. Okay, so you're going to get something like this at t equals 0. And then it decays exponentially. Okay, now this graph is if you have a CMOS MOSFET. Okay, now if you have a power MOSFET, it does this. It lingers, it doesn't turn off, and then it does that. Okay, so let's go ahead and see if we can do a simulation of that so we can see the difference. Okay, so in this case, the current going through the gate, CGS, is the same current going through R18, same current going through V2. So here I can I'll put this statement here to display the current going through V2. Remember, this current is the same as that, and it's the same current going through the gate. So let's see the difference between a power and a CMOS. Okay. Okay, so as I mentioned, at t equals 0, right there, you can calculate. In this case, I had calculated that the current was going to be 10 divided by 18, so about half an amp. Okay, so the peak is 500 milliamps, half an amp. Okay, and if you notice, here's the yellow, that's the CMOS. This would be the power MOSFET. Again, during this plateau, you also have a plateau in current. Okay, you get this little dip in there. So here's a big difference. Okay, so let's look at that a little bit more. Okay, and kind of use these to our advantage. Okay, basically we want to do, when you're doing power MOSFET, sometimes, especially if you're doing high voltage, high speed, switching. Okay, you want to know, or you want to quickly estimate switching times. Okay, in this case, the fall time. Okay, now you can do simulations and do that, but you don't get a feel of what's actually happening. Okay, so what I'm going to do is see if I can derive an equation, and hopefully this will make sense. Okay, so I'm kind of using like a small signal model, or pseudo small signal model. Okay, so I went ahead and this is my V drive. Okay, my 18 ohm resistor. Okay, and I'll explain this in a little bit. Okay, and this, I'll just say that it's a my small signal model for the time being. Okay, so this would be the gate, drain, this would be the source. Okay, what's different is I've connected here the drain through the 28 ohm resistor and a source 125 volts. Okay, so we know that the drain will have 126 volts. Okay, and as this transitions or goes from 0 to 5, this the voltage at the gate kind of stays at a plateau. Okay, and this voltage V6, it's the Miller voltage, V Miller. Okay, and what I did is I went ahead and kind of picked, and let me go ahead and take this off, redo the simulation. So it'll be a little bit more clear. Okay. Okay. So now knowing that the Miller plateau, during that time, this thing is switching. In other words, the voltage from the drain is dropping from 125 to 0, and that this time corresponds, lines up very nicely with this as well. So the voltage of the Miller plateau changes. Okay, it changes approximately from 4 to almost 8. Okay, so what I'll do is I went ahead and picked probably the center. I'll say 6 volts. So I'll assume that the Miller, just pick the middle part, approximate it, and I'll say that it's that when this is transitioning, that the Miller voltage at the gate will be 6 volts. Okay, so I think I already set that up. Okay, so here is some of my statements or assumptions that I can make. I'll say that the Miller cap is, or voltage, 6 volts. Okay, and here's another assumption that I can make. Let me back up here. Okay, so basically the voltage is here. Okay, right there. I'm saying that this is 6 volts. Since this is constant and it's not changing, okay, basically the gate is not moving or changing. So by that statement, I can say that the capacitor from the gate to source has no delta change from the gate to source, and therefore no current flows through it. Okay, let me make sure that I got this correct. Okay, since this is stable and this is not moving, that means that there's no current through here. That's the assumption, no current. Okay, since this is fixed, or at least that's the assumption. Okay, but at the same time that this is fixed, what did I say about the Miller cap? This node is dropping, or is changing from 125 volts to 0 volts. Okay, so this is stable, no change here, so there's no current here, but there is current going in this direction. Let me put this in red. Okay, so basically what I want to do is I want to make sure that I can calculate what is the current going through the gate cap. Okay, so by that statement I can then use this statement. Since I know that the capacitance, I know what it's changing, there's a delta change in the voltage in the Miller cap. Okay, no current here, but there is current through here. So this current that's going through the Miller cap is the same current that goes through our gate and through the drive. Okay, so here's my other assumptions. Okay, so I see Miller. Okay, then I can say that it's the same, or it's going to be equal to the current through R18, which is what I've said, and it's going to be the same through iDrive. Okay, so knowing this, then we can calculate the current through R18. Since this is 10 and this is 6, then we know that it's to calculate the current through the resistor and therefore the current through the capacitor. We know that it's V drive, in this case is 10 volts minus the 6 volts divided by 18. Okay, so we have two equations. We have this equation, and then we have this equation. Okay, so now we can marry them together. Okay, so put together. Here's the second equation. Here's the second first equation. Here's second, first. Solve for dt. Okay, so now we have a general equation to quickly calculate the fall time. Okay, so basically it's the capacitance between the gate and drain multiplied times the voltage from drain to source times the gate resistance minus your drive minus your Miller voltage. Okay, so we have that equation. Okay, so now let's go ahead and use the example that we're using. Okay, well, we know that the CG CGD is 15, VDS is 125, and our gate is 18, and your drive is 10 and 6. So you end up with a fall time of 8.43. Okay, so this should be the fall time between 90%, 10%. Okay, so let's see how that works out. Okay, so let's do this. 125 times 90%, 112. Okay, so let me go ahead and change this, the shape, back to that cursor, and I'll go position, and I'll say find Y value at 112. What up here? Okay, do this again. Position 112. Okay, and then would be at 12. Okay, so this is the 10% of VCC, and this is 90% of VCC. So we take the difference. What do you know? 8.52. Let's see, and I calculated 8.58. No, 43. Okay, so that's a pretty good match. Okay, so when you have a high-speed design, obviously you want to make things faster. Okay, so instead of using the SPI simulation and trying to vary things, you can look at the equation. Okay, now you have something that you can look at, and you can say, okay, oh, what can I do to reduce DT? Basically, in other words, how can I speed things up? Right? So now, hold time. Okay. So now we can look and see, in order for the fall time to be reduced, in other words, make this thing smaller. Okay, we can see that one of the things would be is your CGD, if it's smaller, it would make your fall time. So this is a very important equation, in that if you want something fast speed, okay, you need small meter caps, or CGD. CGD controls the fall time, basically exclusive only on this. Okay, and of course your VDS could be smaller, but this is, you're basically tied to that, to your design parameter, so you may or may not have control over this. Okay, but you can see that your gate, you do have control over your gate. Okay, meaning that you can reduce your gate. If you reduce your gate resistance, it actually speeds things up. So that's the things that you can do looking at the numerator. But if you look in here, there's also stuff that you can do in the denominator. Again, this is kind of set already and is dependent on the device or the MOSFET that you're using. But you might have control over the drive. Okay, so, and look in the equation, let's say we wanted to make this 4 divided by half? Well, the simplest thing would be to change this to 9. Okay, so let's see if it follows. Okay, change that to 9. The simulation. Okay, so here's my 10% and the difference 4.3. Okay, so that's what I wanted to show. So it matches my assumption. Okay, so now I made a statement that how fast this thing drops or falls is totally dependent on your gate. Okay, so how can I verify that statement, or at least loosely state it that it follows that statement? Okay, so let's do this. Okay, let's go ahead and add an external Miller cap. Okay, I'm going to go ahead and connect a capacitor from drain to the gate. So this is an external Miller cap. Excuse me. Okay, so let's go ahead and say that this is 2 pico, and I want you to see how this reacts by adding more Miller. Okay, doesn't change. I don't expect it to change this part of the ramp or this part of the ramp, but I do expect this to elongate. Okay, so let's see if it's correct. Okay, and how we're going to do that. So we'll do a sweep parameter. In this case, it's C1. Okay, and we started out with 15, so we'll the internal one. So we're going to add 5, 10, 15, 20, 25. Okay, so let's see, what do we get? Okay, and mind you, this is with the 9 ohms at the gate. Okay, so here we go, and if you notice, there is a change here, but only in that it changed the time that it transitioned to the Miller cap. But other than that, these have the same shape. In other words, if you were to measure from here to here, here to here, and so forth, they would have the same. But you can clearly see that it didn't have any change here, and there's no change in here, but it does change during the Miller cap, and as well you can see that. So what happens is, by adding more capacitance, you actually slow it down. Okay, you're elongating this. Okay, so what happens if, let's say, we do the same thing to the gate? How does that affect the Miller plateau? Okay. Now, since we have 245 here, let's change that a little bit. Let's change them from 100 to 100, maybe 250 pico. Okay, so now we're changing the gate to see how that affects our the way it discharges. Okay, it doesn't show it too much, but this doesn't change as much as you would have thought. But if you notice here, it delays this, and there's more of delay over here. Let me add some more cap. Let's see, 500. Let's say 750. Okay, now remember, this is a huge change in caps, in capacitance, as opposed to the Miller cap. Okay, so if you remember, this part changes quite a bit. Okay, now you have the first interval changes, but in reality, if you look at this, it didn't change that as much. And remember, we're changing by 250 picofarads. That's huge. So it doesn't have, adding capacitance from gate to source doesn't particularly speed up this or slow down your drain to source as it does more the delay time, but it does change the first, and it changes first, second, third, the third interval. So anyway, that's what I wanted to show, that as far as delay time, the Miller cap by far has more effect versus a small change in changing capacitance. Okay, so hopefully, I know this is quite a bit. Hopefully it makes sense. And if you have any questions, feel free to drop me a email at my or post questions on my video channel. Thank you for watching.